Well, good morning, everyone. I'm Sam. I'm a computational physicist at the University of Rochester, and I'll be talking to you today about simulating inertial confinement fusion physics in Julia. So the package that I wrote is called Cygnus. It's recently developed multi-physics code that we're using to study physics relevant to inertial confinement fusion, often called ICF. Simulating ICF experiments is a significant challenge, even in 2D, due to the multi-physics nature of implosions. So we have shocks, thermal conduction, radiation transport, and a whole host of different physical processes. Typically, these ICF simulations are done in large-scale codes written in Fortran or C++. And here we have Lawrence Livermore lab uses Hydra. Our lab uses Draco. Los Alamos has X-Rage. And then there's also Flash, which is a pretty common astrophysics code. And Julia, as we all know here, offers a compelling alternative that combines performance and productivity. And so Cygnus has been serving kind of as an extensible library to experiment with algorithm development and multi-physics code design. The end goal is a full-fledged HPC code to study relevant physics for ICF implosions. I'd like to thank my collaborators, some scientists at the University of Rochester, and a grad student that's working with me. So we'll go over a brief introduction to inertial confinement fusion. I'll mostly work with pictures here. So there are two main approaches to ICF. We have direct and indirect drive. On the right, we see indirect drive, where we have a whole ROM, which is a gold can, you'll see here, and they shoot laser beams into the edges, into the holes on either side. And what this does is it creates, it essentially ablates the gold on the inside, creates X-rays, and drives our little target in the middle inward. In direct drive, there is no whole ROM. Instead, we just shoot the capsule directly. The idea is to drive the capsule and implode it. So ICF implosions compress spherical targets filled with deuterium and tritium fuel in 4 distinct phases. So in the first phase, we have uniform illumination. So here, if we think about the direct drive case, your lasers directly illuminate the outside of your target. This is a plastic sphere. So you have the plastic melting on the outside. It drives this capsule inward like a rocket. The next stage would be compression. Here you have the shell continuing to move inwards, and you have a corona that starts to form on the outside. This is a plasma now. Then we have ignition, where the center of the target gets hot enough and dense enough to actually create fusion. And then once that ignites, then we burn, and we release all sorts of energy. So the Laboratory for Laser Energetics is a Department of Energy and NNSA funded lab at the University of Rochester that studies direct drive ICF. There's approximately 400 scientists and staff with about 100 students in all levels, including high school students, all the way up to PhD students. Shown here in the top right, we have Omega is the name of our laser system. We have 2 different laser systems. Our primary one is here. It's called Omega. There are 60 laser beams that symmetrically illuminate a target at the center of a target chamber. And on the left here, we have Omega EP, which is a short pulse laser, which we use for other focused experiments. If you want to study laser fusion, lasers, or higher energy density physics, this is a place to come. So if you're curious, I would recommend checking out the link here. So Cygnus, this Julia package, is being used to study the impact of defects commonly found in these targets. Here, this is a schematic of a typical target that we shoot. This is a sphere, so the outermost layer is plastic, carbon and hydrogen. And then on the inside, we fill it with deuterium and tritium, and we freeze it so that it forms a layer of ice on the inside. And then we have a region in the middle that is vapor. And the diameter is approximately 1 millimeter, just to give you a sense of scale. Some of the things we have to worry about, there is ice inner surface roughness. We have gaps between these interfaces. We have defects on the outside like surface domes. We have bubbles inside the ice, and we also have defects inside the shell. So this is an example of a shell that has been cut apart, and you can see a slight defect on the inside. And the reason these are important is because they cause our implosions to become less uniform. So anything that's wrong with the target will get amplified and degrade any potential yield at the end. So one of the things we can do is we run high-resolution axisymmetric wedges to determine performance degradation prior to peak compression. So what all this means is we don't simulate the whole thing all at once in this case, and we just focus on a particular region. So we'll look at this section here, and then on the right here, this is an example of a simulation domain. So here we have a layer of plastic on the outside, a layer of ice, and then gas on the inside. And on the right here, this is just vacuum. So there is a tiny surface dome here for scale, just to give you a sense of how big these things are. So, they're very tiny. They're only about a micron high, but you wouldn't think they'd have a big impact, but they do. Because this is axisymmetric, we assume an axis of rotation or symmetry. So this is run in 2D. And we need sub-micron resolution to track shocks and waves created by this defect. So here's an example. We zoom in, and we have a slight defect here. And if we advance further in time, we see that when the laser hits the outside of the target, it launches a shock wave, and we start to see this is the defect and all the perturbation that's created by this. So I'll show a movie here in a second. So the color of these pictures is indicating the density of a particular material. So we'll go ahead. Again, here's a result from a simulation. We have a defect here. This is a plastic layer, a layer of ice, and gas on the inside. And the laser beam, it will be coming in from the right. It will melt the plastic and drive a shock inward. We can see multiple shock waves, and then obviously the impact caused by the defect. So what is happening here is we have, this would be the dense shell, and we see all sorts of instabilities form because of this tiny defect. And it ends up later on in the implosion, when we get to where we want to compress the gas in the middle, we have holes that form, and we no longer get ideal compression. So this is a bad thing. Simulating these is a significant challenge, even in 2D. Some of the relevant physics, including multi-material hydrodynamics, so we can capture shock waves, material interfaces, instabilities, like Rayleigh-Taylor and Richtmeier-Meshkov. Thermal conduction for laser ablation. Laser light propagation, how we deposit the energy. Ionization and radiation, so the coronal and core emission. Particle transport, we have alpha particles and neutron scattering. Complex equations of state, this is relating pressure, temperature, and density, and much more. But the nice thing is we can still produce valuable research without adding every possible physics process thrown in. So we can just use a small subset, and this is where Cygnus comes in. So Cygnus is a new high-order multi-physics code for targeting physics studies relevant to ICF. And at a first go, we have high-order fluid dynamics. We're solving the Euler equations. It currently is for a single material, single temperature. It uses the finite volume method with arbitrary 1D or 2D block structured grids. It uses a couple different Riemann solvers. If you're not familiar with those, don't worry about it. It's just a way of solving these equations. And then we have multiple orders in space, second, third, and fifth, and then third order in time for Runge-Kutta. For thermal conduction, we assume Spitzer conductivity. We use an implicit solver. There's two different methods. We use a backward in time, central in space, or we have the alternate direction implicit solver for 1D and 2D. And then there is a semi-implicit 2D solver under development, and this is designed to run either on the CPU or GPU. Right now, we assume an ideal gas equation of state, but tabular EOSs are on the roadmap. So here, when you have complex materials like aluminum or plastic or gold, we need to look up from a table how this material interacts, as opposed to just using the perfect gas law. The laser is currently mimicked using an energy deposition source term. This is kind of a hack, but the way to do it precisely, according to physics, is to use ray tracing, and this is something that's currently under development. And then for the coupling between these different physics packages, we use Strang operator splitting. This is essentially just a divide and conquer approach. So the idea here is that we want to use Cygnus as a library and add additional physics with new modules or types by users or new developers. So the hydro and thermal conduction modules have different requirements and parallelization strategies. So for the hydro, we use a block-based shared memory threading. This is a simple approach where you just divide your domain up into blocks, and you have halo regions in between where you exchange data in between each time step. This is a simple to map to MPI. Right now it's shared memory, but you can move to MPI for domain decomposition. For the thermal conduction solver, this is a diffusion approach. The primary mode is an alternating direction implicit split method. So here we do threaded sweeps across. First you do across column, and then you do row, and you can switch back and forth between what order you're doing it. And so here we are just solving a tri-diagonal system of equations for each row and column, and you can thread across that. Efforts so far have been to improve on-node performance, but the plain model is to use 1 or 2 NPI ranks per node and then do threading from there on. Domain decomposition will be provided by the MPI haloarrays.jl library. This is a registered package that I wrote about a year ago, and the basic goal of this is to make it easy to do halo exchanges for arrays of arbitrary size. And you can do this 1D, 2D, or 3D parallel topologies. Right now it's restricted to Cartesian, but you can choose arbitrary halo sizes depending on the order of your solver. So here in the picture we show for 1D with a halo region of 3 cells. You can see that here in gray. And when you're syncing the halos between 2 different domains or 2 different processors, you do an exchange, and this library makes it very simple. So here's a pseudocode. You can look online to see the details, but essentially you have to create a topology first to tell the code what the decomposition is. So here we're splitting the domain up in 2D, 4x4, and we're going to use periodic boundary conditions in both dimensions. And you specify how many halo cells. This is fixed for all the domains. It can be anything from 0 to n. And then down here we're just creating a simple halo array, 200 by 200, and you pass it the size of the topology and the halo. Then you do all sorts of complicated things. When you do accesses, it's like a normal array, and it will be computing this. This is an indexing on the current rank in an MPI setting, and then whenever you want to do the halo exchange, you just call the update halo, and it will do this for you. Laser ray tracing is currently under development and should be added in the next few months. The interesting thing about ray tracing in a plasma physics setting is that it's not like computer graphics, where we don't have an accelerated bounding volume hierarchy to go through. Rays have to propagate through the mesh 1 cell at a time. And they have curved trajectories. This is defined by a density gradient, electron density gradient. So here in the picture here, I show there's a linear density gradient in the heat map. So it's increasing as you go to the right. And it forms something called a critical density. This is where laser light cannot propagate past a particular density of electrons. And it causes these rays to refract and curve. And so here, you've got rays that are entering the domain in the lower corner, and they're colored by the cell. So it gets a new color as it moves through a particular cell. And depending on the velocity vector of these particular rays, you get different trajectories that curve. And as it does that, it deposits energy into your mesh. And this is how you get a source term that drives your particular problem. The tricky part here is parallelization. Do you do domain decomposition or duplication? Primarily, you do it threading on a particular node, and then you communicate with your surrounding nodes. So this is a work in progress. Optimizing on-node performance of existing physics models has been the primary focus so far. So we're working on a semi-implicit model for a diffusion solver. This does thermal conduction and eventually also does radiation. But this will use the same data layout as the hydro, and this is favorable for GPUs as well. The parallelization strategies for hydro, the data layout, I've tried a couple different approaches. One is splitting it up into blocks, and one is using single arrays and threading over that. And I'll go over some of the different types that I've used. So thus far, the hydrodynamics portion takes about 60 to 70% of the total runtime. And how do we optimize this? And so one of the issues here is that finite volume methods are inherently memory bound. So we're going to go over finite volume in a nutshell. You get a crash course on how you do finite volume. So it's a robust method to simulate complex fluid flow in arbitrary geometry. So the picture I'm showing here is an example from an integrated test that does the Kelvin-Helmholtz fluid instability. So you have a shear layer form. You have velocity going to the left in the center and to the right on the top and bottom, and you have some sort of sinusoidal perturbation that causes this roll-up to happen. And we're coloring it by density. But the main point is if we zoom in, we see that it's defined on a grid. And we zoom in even more, and we have a quadrilateral of arbitrary size. So in the finite volume method, you have, this is a quadrilateral, you have normal vectors that define the edges, and you store your state at the cell center. And when you do this for an unsteady problem, you want to see how this state in the middle, in the cell center, changes versus time. You need to know the fluxes of material across the edges, and you need to know if there's any source terms defined in the middle. So we advance this in time by using a multi-stage Runge-Kutta algorithm. This is pretty common. This is a third order version. We're going to advance from time step n to n plus 1. So there's 3 stages. The first stage we show here, second stage, third stage. The point is, without getting tied up in all the math, we have to figure out the derivative du dt 3 times. And how do we do that? Well, I just showed a really basic, we'll walk through it a little bit. So as we integrate, so here's we have a type that defines your Runge-Kutta struct. And we want to integrate it in time, and we're just doing a simple loop over all of the indices in the domain. And then we call this du dt function, and we do this 3 times. In between, we have to do a halo update where we exchange data with our neighbors. So first, we store the fluid state at the cell centers. And so that's what U stands for here. We're just storing pressure, density, velocity at the cell center. A lot of times you might see, if you're familiar with this, you can work with either conserved or primitive variables. It doesn't really, for this talk, it doesn't really make a difference. But the point is we're storing it at the cell center. Next, we have to figure out what the value is at the edge, because ultimately we want to find out the flux of material that goes across the edge. And we do this via higher order methods, and we get when we reconstruct it, we use a stencil similar to this one here. We ultimately want to find the value at the square, but we need the values at the circles to do so. And when we reconstruct it, we get what we call a left and right state. So we have left on this side and right on this side. And if common methods include muscle or Reno. And here, in terms of Julia, it's just passing it the cell-centered values in a particular stencil like this. Then we have to compute the flux of material across the edges. This is just calling a Riemann solver. So here's the math version and the Julia version. We just pass it the state on the left and the right side of the edge, and then we give it a Riemann solver. So here, these are different types of solvers that you can do, but in terms of the function, it doesn't matter. So these Riemann solvers take flow characteristics into account, things such as subsonic or supersonic flow, rarefaction waves. But the point here is that these are not traditionally flop intensive. They're more memory bound. And the final stage that we need to do is we have to sum up the contribution from all of the edges. So we just got the fluxes, the F values for each edge. We sum them up and divide by the volume. Now we know how the state changes in time, or du dt, and this is what we use inside the multi-stage Runge-Kutta scheme. The important thing to note here is that this is a cell-centered quantity, but the flux values are edge-based. And why does this matter? It matters because of memory access. So I've tried 3 different approaches so far. We have simple multi-threaded loops, block-based task spawning, and then we have what's called a local stencil approach. The issues with the first 2 is they're memory bound because we have to use intermediate storage arrays to store data along the edges. In the local stencil approach, we create a new type and compute the entire cell at once, as opposed to looping through and doing things for each edge. So the first approach is pretty simple. We just use a loop vectorization macro at t-turbo, and we have a nice fast parallel loop. And we do this, so this is one of the stages. And this works pretty easily, but it doesn't always scale well because of memory access. So the next strategy was to do it with tasks and blocks. So each task we do, we spawn a new thread, but it still uses intermediate arrays to store edge data. So this primarily required a new array type, block halo array. These are NUMA aware allocated. And in terms of adjustments to the code, it was pretty simple, just a little bit more cumbersome due to having to know which block you're in. And here's some pseudocode. You basically loop over the number of blocks and you spawn a new thread for that particular block. And inside that, you just call the 4 different tasks that you need to do to solve the problem. The final version moved to a local stencil type. The emphasis here is that we only want to read from the global data once. So we create a stencil for each cell, advance the solution, and then parallelize across cell indices. This eliminates intermediate arrays, and this is an attempt to reduce the dependency of memory bandwidth. But here's the kicker. This method actually duplicates work, but it ends up being faster because in this method, all 4 edges are computed in one pass. In algorithms 1 and 2, edge data is shared, so cells only have to compute 2 edges. So it's kind of counterintuitive, but we end up with a faster algorithm when we stick everything in a new struct. So the stencil type contains all the data required to advance the solution forward in time for a single cell. Here we stick the data in basically a S matrix with S vectors. There's a few other terms here, but the idea is that we want everything to be static so that the compiler can optimize. And we do threading across cell indices. So here, obtaining peak performance depended critically on using the @batch macro and the underlying pointer arrays that it casts everything to. So again, here we're just looping over the cell indices and parallelizing this way. And this particular function computes everything we need. Strong scaling benchmarks show improved performance for the local stencil method. So this is a fully integrated test where we're doing a blast wave. So you just think of a square domain. You dump a bunch of energy in the middle and it just creates a blast wave. About 4 million cells, and the timing here I'm showing is only from the hydrodynamics portion. So the machine I ran this on has 16 cores. Once you go above the number of cores, if you're trying to use hyperthreading, you're not going to get any advantage. So the old algorithm was block-based. Here we see the scaling tend to fall off a little bit. The idea here is obviously you want the ideal where you add 2 cores, you get a 2x speed up. And this local stencil method, we get about 98.5% parallel efficiency, which normally when you see these strong scaling slides, they'll do it on a log-log scale to hide the fact that they're not quite ideal. So I was pretty happy. We can also look at this using an empirical roofline model. And the idea here is you want to characterize how well your algorithm is utilizing the machine that you're on. So first step is to know what your machine can do. So I use the empirical roofline toolkit from Berkeley Labs. This will run a suite of benchmarks and give you some bandwidth and floating point operation numbers for your machine. So here, each roofline tells you the memory bandwidth of your hierarchy of memory. So you have DRAM, your L3, L2, and L1 cache. And if you're on this side of the dashed line here, it means you're limited by bandwidth. And if you're on this side, it means you're limited by floating point operations. So an optimized approach is as close to the roof of your particular memory hierarchy as possible. So in the new method, we are above DRAM, which means that we are benefiting from some cache reuse, which is good for scaling. So I'm at my time limit, so I will end it there, but thank you for your time.